myself right now.
We're on? Okay. Great. I'm just doing. Good evening, everyone, and welcome to our presentation on high-speed development, writing fast code and writing code fast. My name is Jenny Tessier, and we will do some intros, see up on the screen. So I manage campus recruitment at IMC. I've been with IMC for 4.5 years. I studied HR management and psychology at University of Sydney. What I love about IMC, I'm quite passionate about early careers and early career recruitment, but what I specifically love about IMC are the people that I work with. So working with really smart people, and no 2 days are ever the same. They're busy days, there's opportunity to make fast impact, but we generally really do love what we do. And when you're working with people who are passionate about what they do and generally do really love coming to work every day, it does make it a pleasure, and it does make it a really exciting place to be working. So our guest speaker this evening is Dave Gittins. So I'll let him do his intro.
Yeah, thanks, Dan. Yeah, so yes, I'm Dave. I started out studying science, physics, and started out in academia, and then aerospace engineering for a while. Found my way into software engineering. I've been with IMC now for about 6 years. Started with a software developer role in IMC. And now I'm the data team lead, so a bit more team and project management kind of role, and coordinating everything. But yeah, IMC is, I think, definitely the best job I've had. I think the thing I love most about IMC would be just the sheer amount of stuff that I learn every year, which shows no signs of slowing down as we keep doing new things. Okay, so that's us. I'll get onto the main part of the talk. So just before we get into the meat of the talk, I've got a bit of an introduction on what IMC does, what market making is, and why we need to be fast. So there's a couple of short videos just to set the background for the rest of the talk. So I'll start with this one, which you should be able to hear.
What is market making? When someone wants to buy or sell a financial product, they need to make their way to an exchange where buyers and sellers meet. The price they can trade at depends on the supply and demand of the product at the moment, and this is translated into the bid, price to buy, and ask, price to sell, spread. If there are limited counterparties to trade with, then it may not be possible to buy or sell the product, and the product is now considered illiquid. In order to guarantee liquidity, exchanges ask professionals to continuously provide a bid-ask spread to the market. In other words, these professionals make markets, hence the origination of the term market makers. Market makers do not have an opinion on whether the price of the product should go up or down. They make money on the difference between the bid and ask price, the spread. When a market maker trades on either side of the spread, they take a position in the market, which is a risk. They will try and find a way to offset that risk by, for example, hedging the position with a different product. A market maker must therefore not only understand the product they are making markets in, but also the relationship with other similar financial products. Over time, competition and technology have significantly changed the job of market makers. In order to continuously provide competitive quotes on multiple exchanges and multiple products, computers running trading algorithms are needed, along with electronic exchange connectivity. Market makers need to continuously invest in both technology and people to remain competitive and contribute to efficient financial markets. This is something IMC is committed to. While these technology advancements and competition have made the job of market makers significantly more complex, for investors, those wanting to buy, sell a product, they have provided real benefits in reducing their transaction costs to buy-sell, for example, through the tightening of the bid-ask spread.
Okay, so hopefully that gives you a good idea what our business model is, what we go out there and do. We run automated trading systems that are trading pretty much around the clock, offering prices to buy and sell as explained in the video, and making our money on the small difference between those. So you can imagine doing that across a wide range of products on a lot of different exchanges worldwide. There's a lot to look after and manage. But this talk is mostly about the speed side of things. As a software developer in this kind of industry, you spend a lot of your time balancing a few different things. Firstly, just being fast. It's a very competitive landscape out there, and if we can get our orders out or move our prices or whatever it is we need to do before the competitors or before the opportunity is gone, that's absolutely critical, and very small differences in how fast the software responds can make a very big difference. But also just the scale across a range of products. We may need to be balancing positions in one versus another. So there's a different kind of software challenge where information from one trading product needs to be shared to other systems trading other products. Fitting volatility curves and risk measures across a range of portfolios and all these kinds of things. And being able to adapt quickly and try new ideas in that space is equally important to be able to keep up with competitors. And then finally, of course, managing the risk of all of this. Automated trading systems have to be very closely monitored with layers of checks to make sure that they're only doing what's expected, and they'll stop as soon as they're doing something that they're not supposed to be doing. So it's a pretty exciting space to be working in. So getting back to the point of this talk then, the two different kinds of being fast, writing something that's going to execute quickly, but also being adaptable with our code. So I wanted to talk a little bit about how we achieve both of those things at a high level. What kind of habits and areas do we focus on to achieve these? All right, so part one, a lot can happen in 1 millisecond. So let's take a bit of a closer look at the environment our software would actually be running in. So as any company in our business would, we run our trading software on servers that are in data centers close to the financial exchanges. Pretty much all exchanges will have a data center where you can do this, and you get as close as possible. Sometimes in the same building as where the exchange itself operates, or otherwise nearby. So you rent space there, and that's where you put your servers, and that's where our trading software will run, and we would operate that remotely. So this would be the typical kind of setup. The trading exchanges always run a piece of software called the matching engine. So the point of the matching engine is to keep track of all the incoming orders and prices, and figure out who's traded with who, match up all the information, and send out the updates. So if I'm offering to buy something for 10 and you're offering to sell for 11, there's no trade. If I change my mind, I'm willing to buy for 12, well, now a trade can happen, and we've matched. So the matching engine keeps track of all of that, and it's constantly sending out market data updates to everybody and receiving order instructions in return. So this is all just network data that's constantly flowing. So how does the information get to us? Through some kind of infrastructure, which varies a lot from one exchange to another. It could be going through various layers of equipment on the exchange side, down the corridor and through some more equipment. And finally, we get to the place where we plug in our network cable to our own network switches. So all the market data updates will pass through our equipment, and finally reach the trading servers. And then we get into the software that we'll look at in a bit more detail on the next slide. So a lot of our job when we're dealing with this high-speed stuff is around the network packets. Ultimately, it's a network packet that comes in, and it's a network packet that's going to come out from our server if we decide to do something. This network packet might be telling us that someone's changed a price or a trade has happened. Maybe we're going to send an order in response, or maybe we won't, and we'll send nothing. But the internal latency is what we call the time difference from here to here. So it's internal to the trading server once the network packet has arrived. And that's the one that's obviously most directly under our control as software developers. The data's arrived here. It's up to us to get it back out as quickly as possible. And then orders come out this way, again, through the network switches, through all the exchange infrastructure, and finally reach the exchange. So the external latency is the measure of how much time it took for this information to reach us this way, and for our order to get back out this way. So that's not directly under the control of the software. However, there is a lot that we would still do in the software development side to influence this. For example, it could be that if you send your orders in a particular way, you construct your network packets in the right way, they're going to get through these switches more quickly. Maybe even on the exchange side, although we don't know exactly what equipment they're using, or we may be able to guess, or they may have some information about it. We may be able to, again, change how we're sending orders so that it's going to pass through here more quickly and maybe get there before the competitors, or even sending a different kind of order message. So there's a lot of factors in that external latency that still come into the software that we develop over here. Similarly with the market data, maybe there's multiple ways you can request the market data from the exchange. And if we do it the right way, it could get there slightly sooner. So we need an appreciation of the whole picture here. And it's different for every exchange, and they change over time as well. So there's always changing selection of challenges and places to try and optimize. So then looking a bit more inside the software then, what do we need to do to really minimize the time between getting information and getting something back out? So the first place to start would be the network card itself. Probably the most obvious thing you can do to save time here is to get the operating system out of the way. When we are trying to respond in microseconds or even less, you can't afford the time for the operating system to tell you that some network data has arrived and maybe there's an IRQ and a context switch, and then you read the data and you go from there. That would waste far too much time. But network cards designed for this kind of application let you interact directly from your software to the network card instead. So you're doing direct memory access to the card. It tells you there's some data available, and you grab it as soon as you can. So that's the first area that we have to pay attention to. And we'll get the data through the networking API as soon as it's available. And then we come to the Exchange API. So we've managed to get the data out of the network packet, or maybe in the other direction where we need to encode it in exactly the form the Exchange needs. Now here again, every Exchange is different. They all have their own protocols, and they're all different, and some of them are very odd, and they may not have very good documentation. So this actually can be very frustrating and also incredibly valuable. Frustrating because we have to implement for all of these exchanges individually. You have to change things again when they decide to migrate to a new version. There's a lot of code to write that could be fiddly or unclear, and you have to experiment and see if it's right. And probably over all of its history, I would say IMC must have written implementations for, I don't know, about 1,000 exchange protocols or something like that. It's a huge number. But then why is that incredibly valuable? The answer is because there's a lot of scope there to, again, do the job better than somebody else. Maybe we can save some time by having a faster way to turn some string into the number that it represents, or figure out that some bits of the data we can skip over or process more quickly, or a different kind of message that doesn't take quite as long to read. And on the outgoing path, could be that we have a faster way to encode our order message into this particular Exchange API that doesn't take so long, or we can prepare some of it in advance or something like that. So in other words, dealing with the Exchange protocols is actually just another battleground on which we can compete for latency with our competitors. And that can be some really fun discoveries you make in that area. So once we've decoded the actual information, now we know what's happened. There's been a trade or an order or something like that. Then the general structure would look something like this. First, the market data processor deals with the new information. Okay, which product is this for? Is this one we're interested in or not? Do we need to update our state of what the current prices are? And do all of that basic handling. And then you move on from there to the opportunity checker. So this basically is where we're going to make the decision, are we going to respond to this or not? Is there an opportunity here to make a trade for something that we think is worth the money that's being offered, or do we have an opportunity to move our prices or whatever it might be? So here you can imagine there's a real balance to be struck between how much complicated logic you can put in here to make a smarter decision versus how quickly that's going to be able to respond. The most obvious opportunities in the market would be where you can buy something for one price and immediately sell it for a higher price somewhere else. And that doesn't need any logic here. It's just whoever gets there first will be able to make a profit on that. But something much more subtle where we believe it's worth buying something now to sell it later or to sell another product could be more complicated, or deciding that we're going to shift our valuation very slightly and move all of our prices across 40,000 products, as mentioned in the video. So one way we can tackle that trade-off is by just designing what's in the software here to be able to apply some simple rules that are going to be valid for a short period of time, for the next few seconds, extrapolating from where they are. And then in between the events coming in, it can be updated with new information from something more complicated at a higher level of the software that's keeping track of the market more broadly and feeds it sort of the next information it needs to prepare itself. So again, a constantly changing trade-off there, and new ideas are always being injected into this part of the code. But let's say we've decided we do need to do something. We've decided our valuation for this product has gone up slightly. Okay, well, what individual orders do we need to place? That's where the order processor would come in, break that down. We had an order to buy at this price. I'm going to move it to that price. We had another order to buy at a lower price, which we're going to move, and so on. So it figures out all the individual instructions we need to send to the exchange. And then this extremely important part, the risk limit manager. So this would be basically the gateway for everything that we're about to send to the exchange to make sure it passes all of the checks that we need to pass. So you can imagine in this environment, if there's some mistake in your software and it's sending the wrong kinds of orders, you could get into trouble very quickly. And there are also a lot of regulations that need to be followed, both from exchanges themselves and from regulatory bodies to prove that you have the right kinds of checks here. So it could be that we're making sure, does this order make sense? If this is normally worth $100 and we're buying it for $2, something is clearly wrong. Let's not send the order. Or maybe we've already sent too many orders without receiving any more information from outside. Time to stop doing anything and wait for updated information. And whatever else it might be. And then it's tempting to say, well, we could send the order out and then apply all of these checks. But that obviously doesn't work, because then instead of it's a bad idea to send this order, it would become that was a really bad idea to send the order you just sent. So you have to have these checks in line. Therefore, making these as fast as possible while making sure they're still rigorous is another really important part of the job. And then finally, the orders make their way out. And then there's some more we can do that doesn't have to be done in line, that can wait until afterwards. Basically just recording what happened. The rest of the trading system, the layers above, they need to know as soon as possible, okay, this order was sent, that order was sent, update their state and do everything else they need to do. But that can come afterwards so that we don't slow down this loop. If this goes wrong somehow and we haven't been able to make a record from here, we always have a record of the network packets we sent. We do also record all of those. So we have an unambiguous record of everything that went to the exchange if we need it. But normally this is how the rest of the trading systems hear about what happened. So that's the basic structure. Of course, there's a lot more complication and fiddly bits in reality, but this is usually the space that we're working in. So we're always thinking about the network packets and getting this loop as fast as possible. So maybe I can just then review some of the key things that we do to keep this latency low in this kind of job. So the first one is know your hardware. So writing software that you think is going to be fast without thinking about the hardware environment is never going to get there. We talked about being able to interact with the network card efficiently in both directions. That's an extremely important part of it. But also just the software itself that's running on the CPU. What's it doing with memory layout? How is it using the CPU cache? These kinds of effects can be very substantial on the latency you can achieve. And then even beyond that, what kind of network switches are we using? Is this the best way to get the data in and out? So when you're working at that level, you're really thinking about not so much abstract software as how to make the hardware do exactly what we want it to do as fast as we can. And That also then extends into FPGA development for cases where we need to be even faster than we can achieve with software. The second point is to measure the right thing. So when you're working at these kinds of latencies, writing benchmarks or other tests to try and measure and micro-optimize pieces of this code are never going to really capture what we're looking for. The times are so small that you can't measure them reliably with software tests. It may only be a few CPU cycles in some cases, and you can count how many CPU cycles, but that doesn't tell you how long it will take either, especially when all CPU cache effects or interactive with network cards are taken into account. So really the only measurement that matters to us is the so-called wire-to-wire. When a packet comes in here, we record when that packet arrived with a very high accuracy clock, and when the packet comes out here, we do the same thing. And then you subtract the time between those. So we can do that in a performance lab in our own office. We can make the same measurement for production systems, and that is the measurement we're looking at, and we optimize the system to minimize that. Similarly, for the external latency, you can try different things and see the effect on the external latency. So having confidence in your measurements, looking at the distribution of them, being scientific about it, very important part of winning in that space. And finally, use the latest toys. So again, it's one of the fun things about the job is playing with all the new technology. So of course, you can buy a faster CPU or a faster network switch, but it's also the software tools. So we generally use C++ for this end of the software development. And as the C++ language has evolved and the compilers have evolved, they've been able to squeeze more and more out of the hardware, and we need to keep up with that, again, because our competitors will do the same. So IMC is always using the latest compiler versions, and quite often has been able to uncover subtle bugs in the latest versions of GCC, for example, and work with the GCC developers to have them fixed. So yeah, and in some cases, the new language features may also let you write some code that is a little bit more readable, shall we say, but can still achieve the fastest result you were looking for, where previously it would have to be some fairly ugly looking code to get to the same speed. Yeah, so those are the main areas of focus when we're really in that speed race part of the software. I'll talk a little bit more later about the other layers of the software stack that are not quite so extreme on the speed. But what about writing code fast? So it's all very well having the absolute fastest system, but if we can't change it, we're also not going to succeed in this market. The markets are always changing. New products are becoming available. The level of trading and interest in different products is always coming and going. Competitors find new ways to do things. Exchanges roll out new protocol versions and new features and even new products. There's so much going on that nothing really stands still. So we need to be able to modify our software all the time to deal with this, even to get into new markets quickly when they become available. And so another big part of the software development culture in this industry would be around that. How can you have a rapid development cycle for your software and be confident in the result? So we can take a look at what the life cycle of a code change is, and I just wanted to highlight the important parts of this that help us to be adaptable and to be able to change code quickly, which I've certainly learned from IMC a lot in this area myself. So you start with some idea of a change that needs to be made, and this could come really from anywhere in the organization. A trader or a developer has an idea, hey, I think we can do this faster, or I don't think this valuation is right, we should be doing this algorithm, or even something more substantial, like we could take this whole system and we could apply it to this product, and I think it's going to work. Whatever it is, Those ideas and requirements are coming up constantly, and then it's just a question of prioritizing what we want to work on. And from there, it's always a collaborative process. Get in a room, get on a whiteboard, although the way things are this year, more likely you get on a Zoom call and talk it through. Talk about, all right, what are we trying to achieve? How are we going to do this? What do we already have? How are we going to test this? How are we going to make sure this works? And that's always part of the conversation from the start. How are we going to test this? You might implement something that looks like it's working, but that's never the objective. We need to be able to prove to ourselves that it's working as part of the job. So from there, write some code. So a bit more on this later, but you want to be able to write the code as efficiently as possible. So, I mean, part of that obviously is just about hiring good developers, but it's also about making sure that the code itself is going to be easy to change. And that's something that can easily let slip if you don't have that culture through the whole organization. If code just gets more and more messy over time, then you end up with areas of code that people don't want to go and change. And then it becomes more and more expensive to modify. So when you're writing code at this stage of the process, you're not just thinking about making it work, you're also thinking about maintaining that quality, maintaining the code in a state that actually can be worked on later. But let's say you've actually got your code change ready to go, or you think ready to go. Then it goes into the automated build and testing system. So the tests are a very heavy part of what we do here. Any code change you make, if you think it might be ready, it can go off to the build servers and go through a whole battery of automated tests. So we use the common idea of the testing pyramid. At the bottom of the pyramid, you have your unit tests, the most numerous, testing just individual parts of the code. And then the layer above that would be the component tests, where we're looking at whole classes or groups of classes that work together as a component. Not as many tests, they're more expensive to write and maintain, but they deal with making sure you haven't broken anything fundamental in that area, particularly when developing new components. And then above that, the more integration level tests, where we run entire systems, start them up and make sure they're communicating properly. Does everything look like it's flowing correctly? Again, much more complex and expensive to write and maintain, and smaller in number, but also part of the process. And this is all automated, so that the whole test suite can run on any change you're thinking of making even before anyone else sees it. So usually some iteration there. Did I break my test? Or even worse, I thought this test was going to break and it didn't. Why didn't it break? Go around this loop. And then from there into code review. So all of our code changes go through code review. You would normally work with someone else in the team, or could be from any other team who's competent to look at the code. Go through it, and the reviewer will be looking for some very basic things. Is it clear? Do I understand what this code change is for? What is it doing? And what are the tests? If you change the functionality and none of the tests have changed, that would be an immediate red flag. Why is the test behavior not changed? Are we not testing this behavior, or did you just do it wrong? So normally code would go around this cycle a few times. You could be sitting at someone's desk and working with them directly on this, or through a code review system like Gerrit or something like that to get the job done. There's some flexibility for different teams to work the way that's most effective for them, but all code is reviewed and there will be a record of that review. So once we're happy with the code and the code review, then it can go into the build pipeline. And again, big believers in the continuous delivery model. So code goes into the build pipeline as soon as it's signed off as being ready to merge back to the main code branch. Goes through the whole build process, and a new version of the code will be available as soon as possible after that. So in some cases, depending on what you're working on, this could happen in a few hours or something like that. And certainly it's not unusual for a change to actually reach production trading on the same day if it's important, and we're comfortable with this whole process. Other larger changes, of course, take longer, but yeah, we're upgrading our software all the time. So the build pipeline for some small projects could only take a couple of minutes. For some of the larger trading systems, it could be longer, waiting half an hour or an hour or something like that. And then FPGA development, of course, if any of you are familiar with that, that takes an awful lot longer because it has to build and optimize all the FPGA designs. But the same process applies. It just takes longer. So in this way, with everything changing constantly, we maintain that adaptability. We look further ahead to pieces of work that need to come up in the following weeks, and basically prioritize where we want to apply this process and keep up with changes. So again, I thought I'd just highlight some of the key things about this that enable this to be fast and enable us to compete in this space. And the first area is really all that automation that I mentioned. Any testing we do that's manual is just not going to fit. Or if all of our tests are automated, then they can all automatically be run on every change that we make, and we can farm that off to racks full of servers to do the hard work for us. Same for all of the building and the deployment process. When the change is ready, there are automated processes to upgrade to the new version the following morning, so the traders will know what's changed, and they can start working with the new version straight away. So just take all the manual work out of this. And that does take a fair amount of effort. You need to treat your build system and the configuration files and the build configuration code as being equally important to the software itself. It's not okay just to have a complete mess for the files and software that run the build process. They need to be kept clean as well, and the quality of those is something that we also rely on. The second point would be this one, writing readable, loosely coupled code. So sounds fairly clear, but really we're talking about fear here. So if you need to make a change in your code, fear is something that's going to slow you down. And the reason that you may hesitate is if you don't really understand the code you're working on, how can you be confident the change you're making is good? Unit test coverage can only go so far. It's never perfect. And when you're dealing with interacting systems, you need to be confident that you understand how the code works. So just paying attention to that quality in the code review and when you're writing the code goes a long way. Is it clear what this code actually does for other people coming in here in future? And that's not usually a case of comments and documentation. They have their place, but what we find is that they also have a tendency to go out of date. It's much more powerful to structure your code differently if it's not already clear to other people how it works and what it does until it is clearer. And that can also be a case of the tools that you choose. We use C++ for the very fastest parts of our code, but maybe things that don't need to be running at that speed can be in another programming language like Java or something like that, where you have more code inspection tools that can help you to understand how the code works. And the same for making it loosely coupled. If you introduce an assumption into your code on some other part of the system, then it immediately makes it difficult to know when you change one component whether it's going to have an impact on another component. Making your classes or pieces of code well isolated where they're not having to make assumptions about other parts of the code is not just sort of clean and elegant. It really does speed this up, because then you know, okay, I can just need to maintain the contract or the interface here, and everything should be good. And then you're less likely to run into an issue later on, maybe after something's been deployed, because you didn't understand about the coupling between two pieces of code. So it's a really important part of the culture for speed. And then the final point is owning your changes end to end. So there's no handover of changes to another team or anything like that. If you're involved in one of these discussions, something needs to get done, then you're the one who goes back and talks to the original owner of this until you understand what needs to happen. You're the one who writes the code. You're the one who gets all the tests working and fixes up the tests if they're broken. You're the one who patches up the build process if there's something that's trying to do that's not working for your change. Get it through code review, deal with the review comments. You're the one who makes sure it goes through the build correctly and that you're aware when it's deployed to production. And you would be the one who goes back to the traders, hey, did you turn that feature on? It should be available today. Are you using it? Let's have a look at the logs. Is it working properly? For the type of people who we hire, that would come very naturally anyway. But it is something that really does save time, again, getting back to the speed aspect. You don't need to hand over changes to a quality control team or anything like that and have to document information at those boundaries with risk of miscommunication and all of those things. You just see your changes through. Okay, so much for writing code that is fast and also being able to change our code fast. But it can be difficult to have your cake and eat it in that respect. So the final part of the talk, I wanted to look a little bit at where these come into conflict, and then again, just a few things that we can do about that. So this is the sort of trade-off we are talking about. We want better latency, a code that's going to execute as fast as possible. We also want it to be easy to change. And there are a lot of times when we can't have it both ways. So one example would be the level of optimization we're putting into the code in terms of just trying to get the CPU to do exactly what we want, trying to get the memory to do exactly what we want. That doesn't always make for the most readable code. So maybe someone looking at this later is going to be scratching their head. That means it's slower to change. It may even be introducing some of those couplings that we don't want to be there because it's much faster if we can just assume this value is always going to be 0, or we're going to find something at this memory location just after this other piece of memory, or whatever it might be. So how can you write that code and still have pieces being well isolated without those assumptions? Sometimes you can't. You have to make a choice in that trade-off one way or the other. Similarly, with the dealing with the hardware, it's much easier and smoother to work with a piece of code that's going through an abstraction layer, isn't interacting with the hardware directly. You can use well-documented standard operating system features to deal with your network communication, for example, as I said at the start. But if that's just too slow, then you don't have the luxury of using any of those. And your code is instead going to be dealing directly with the memory access from network cards or whatever else it is that we're doing. But maybe you don't need to apply that pattern everywhere. You only need to do that when it's actually saving you time that you need to save. A similar point applies to just the general abstractions that tend to come in when you're trying to make your code nice and easy to understand and decoupled. Maybe it's convenient to transfer everything to a common data model, so it works on exchange A and it also works on exchange B. Great, now I can have that market data processor work equally in both cases, or even across 10 different exchanges. That can save a lot of time when working on it because people will be familiar with the data models and how it works. But it takes time to transform something from maybe the data model the exchange uses into our own one. And so if we're really squeezing the latency, we maybe can't afford that. And you have to tweak what your market data processing is doing so that it will fit the exchange's data model instead.
It's okay.
And you can imagine examples like that cropping up all over, where a nice programming paradigm may have to be sacrificed to try and get things faster. High-level languages as well. I alluded to this earlier, where we're using C++. Sometimes, let's say, and if you're not a C++ expert, it can be more difficult to understand what's going on, and it comes with some other factors that again can impact the pace of change. C++ build processes can be slower, they can be fiddly, they can break in maybe sometimes unexpected ways. You can have much more subtle bugs with invalid memory access and things like that, or undefined behavior that you don't even know is there but could cause behavior that's non-deterministic in production. That's particularly scary. And then also the tools that we use development environments, IDEs, and all kinds of tools we can throw at our code. But it's still very hard for them to take complex C++ code and be completely confident what's going on, because the code structure is complicated, and there are macros and templates and all of these things. If you're working in something like Java, you maybe get away from a lot of that. The process is a lot more deterministic. You're virtually protected from invalid memory access and things like that, unless you're doing something particularly sneaky. And the development environments really do understand what's going on in your code. If you can search for where something is used, they'll normally be able to tell you the right answer. And you can achieve much more powerful refactoring with that kind of approach. Even other languages, lots of languages get used at IMC, Golang, and Python, even for some of the analysis tool sets, and Scala, Kotlin, all these things have their places. But ultimately, it's virtually impossible to get to the same latency with anything other than C++. Or going all the way down to FPGA, because you can't just get that real direct hardware control of exactly what you want to be in memory and where. So in a way, being forced to use C++ can also be part of this trade-off, that the code is more expensive to work on and maintain. So what do we do about this? How do we balance this? Well, there are a few things that help with this situation. The most important thing actually is to make the trade-off consciously, not just on a case-by-case basis. See what happens. It's something that should be discussed as part of the design and implementation of a code change. How fast does this need to be? Which area are we focusing on here? Well, is there another way we could approach this that's actually going to be a bit more readable to sacrifice a bit of speed? So having that always in mind is actually one of the most important things, and that's something that we're always doing in the life of a software developer here. A lot of code review will be on this area. This is slightly faster, okay, but is it worth it to introduce this coupling into the code and those kinds of conversations? The second point is about the multiple layers, hence the layer cake here. Where we do need that ultimate low latency, then yes, using C++ and FPGA and those kinds of things make sense. But what we find is that as soon as we can, as we get away from that, we do tend to move into something else like Java, or into, if it's still C++ code, at least into code that's making more use of luxuries like libraries and standardized data models and things like that, and virtual functions and things that maybe have been stripped out of the lower levels. And then as you go higher into the layers of code that are doing things like maintaining our records of our position across multiple products, or balancing risk across different portfolios, or maybe a trading GUI that a trader is going to use, then yeah, you're much more likely to work with those higher level abstractions. So being multidisciplinary and being able to move smoothly across those programming languages and paradigms really helps, and just that you have in mind where you are in that stack. And when you get to the highest levels, maybe things that are not involved directly in the production trading, but are more just general monitoring across systems, looking for issues, or even just doing analysis of data we've recorded, much more something I'm involved in my data team lead role. There again, you may find more things like Python and JavaScript and Golang coming in, or whatever else it might be. So yeah, using the right tool for the job helps a great deal. And then this final one, generate boring, repetitive code. That doesn't mean go to your desk and write code that is boring and repetitive. The point here is that there's a lot of code to deal with things like the Exchange APIs I mentioned before. That's a good example where it is very boring and repetitive. You have some sort of Exchange specification for different message types, and then you need to implement something that's going to take the message types and do something with them. Maybe it's transforming them to some other form or whatever it might be. And this code also needs to be fast. There's a lot of it to write, and it may not be very readable as a result. But what we can do is use a code generation approach to produce that code instead. So you write something that's going to take the Exchange specification as input. These are the definitions of all the message types. And then it generates the source code, the C++ code that is nice and efficient and optimal for you. And then maybe it doesn't really matter if it's very readable, because you shouldn't need to read it. What you need are absolutely bulletproof tests around it, that it's complete and correct and works and is fast. And then you just need to maintain the code generator instead. And actually, we find we can use this approach in quite a few different areas. It could also come up when we're looking at an algorithm that needs to be implemented. Maybe you can express that algorithm in higher level terms that are faster and easier to work with. And then something generates source code that's going to implement them underneath in a fast way. So again, a fairly common technique in the industry, and one of the more interesting parts of the job that we work with. All right, that was it from me. I think it's back over to Denia for a few final thoughts, and then we'll have time for some questions.
Thanks, Dave. Really informative and fascinating presentation. I hope that everyone has enjoyed it. I did want to just give a bit of an update, I guess, from our campus roles, and give a bit of a plug of what we've recently got open and what we still have open for the year. So we do still have opportunities for 2021 grads. The SRE role, candidates may have heard of this role before. It stands for Site Reliability Engineer, and we do still have a grad role to start in February 2021, and that will be joining our Trading Systems Engineering team. And we have recently opened our graduate and summer intern roles for 2021-22. Can you believe we're back here again? We've opened up our roles earlier this year to give candidates an opportunity to learn more about IMC before they apply. So applications will still be accepted up until April next year, but the roles are open now if you are super eager and want to get your applications in. So for our summer intern roles, we have roles to join our trading teams, our software and our hardware teams. This year we're quite excited, although the impacts of COVID have obviously affected us all. We've been able to pivot, and we've got our summer interns starting next week under a virtual internship program, which is really, really exciting. It's an awesome program. Ideally by 2021, end of 2021, we will be back to having face-to-face internships. If not, we're still in a great position where we can offer a fantastic opportunity to run the program virtually. And our 2022 graduate roles. So this probably seems quite far ahead, but this would be for students that will be in their final year in 2021. Once again, we have roles in trading, software, and also in SRE, an SRE role. Now, with our grad roles, we have 2 intakes. We have an intake in February and in August in 2022. So all applications can be made via imc.com under the careers page. But if you ever do have any questions, please do get in touch with our careers team at careers@imc.com. And finally, I just wanted to give a bit of a flavour of, I guess, what life at IMC is like. Now, obviously, these pictures are taken pre-COVID, but, we have a number of different social events. The social events really give us an opportunity to get to know each other outside of work as well, because as you can understand, the working at IMC, a teaming element is so important. So it is really important that we do have those strong relationships inside and outside the office, and we all like to have a bit of fun as well. There's a picture there from one of our charity events. We have various charities that we do support, and this was an opportunity where we could dress up for charity, and sporting events. So we're quite a competitive organisation, so we do have a number of sporting events and competitions throughout the year. I think this one was the Bloomberg Mile, which our team did exceptionally well in last year. This year, our events haven't dropped off. We've still managed to have a number of different connection points across the office, albeit they've all been virtual, but it's really been an opportunity that to ensure that we all still are engaged with each other and still have those opportunities to be able to connect together, because that teaming element is really important at IMC. So that was just to give you a bit of a flavour for those that don't know too much about the culture at IMC, that there's some important elements. So I think now we'll hand over to questions. Are you there, Yutush?
Yes. I'll just read some questions out to you. So the first question was from Ishraq, and he asks, why is there no standardization of Exchange APIs?
Yeah, have we got some questions?
Hello, can you hear me? Hello?
Okay, I think we might have lost you, Tush. So I can actually see from the live chat some of those questions. So I'll start running through them to Dave. So firstly, we've got some questions around the APIs. I might read both questions to you, Dave, and then although they've come in as 2 separate questions, I'll read them both because I think they are connected.
Sure.
Why is there no standardization of Exchange APIs? And then what kind of testing procedures do you go through when implementing an API for a new Exchange protocol?
Yeah, 2 really good questions. On the first one, I think the simple answer is there's really not much incentive for the exchanges to standardize. They're run as their own competitive businesses, and then they know people will need to come to them and do business, but they also maybe see their different protocols and things like that as differentiating factors in their own competitive landscape. Generally, I think exchanges, they always want their software to be in-house and not something that they share. If it's also in a country where they don't really have any competition, they also don't have much incentive to make their API good because they're not going to have a competitor. So yeah, I think that plus the very varied and complicated history of all these exchanges is probably why it's become so fragmented. I'm not sure I know any better reason than that. And then around the testing, this is a really good question. So obviously, if we are writing something to deal with an Exchange API, we have all of our own unit testing, but beyond that, all exchanges generally offer test facilities as well. So maybe at the weekend you connect to a test market where you do pretend trading and data comes in, and then you send your orders against that and see if it works. And there you can really, stress test things. Or what happens if I try and send 10,000 orders at once or something like that? So that's a very important part. And most exchanges would mandate some kind of test as well, where you prove you went through a series of steps and everything was good. And then finally, if it's a new, let's say it's a new exchange or an upgrade, and we're pretty confident, we've been through all those steps. The rollout for real trading is also done in phases. So in the first phase, maybe we would only listen to the market data and we'll just make a note of all the orders our system thought that it should send, do that for a while and check it's okay. And then we start trading on small scale just to make sure all the orders are flowing through, but only small quantities and maybe a smaller number of products. And then, yeah, if something really obscure has happened, maybe you get contacted by the exchange, hey, this looks wrong. You're sending these orders, but this field is not set or whatever it might be. And then you fix it up from there. So mostly all about doing it in layers. That weekend testing facility is something that can also be used at any time after you've written the API, when you're coming up with some of those ideas I mentioned to use it in a different way where you think you can get orders through more quickly. You can always do it in a safe way against those test markets.
Great, thanks, Dave. Next question I think is aimed for me. A lot of HFT firms place a lot of emphasis on academic performance. Is IMC the same in this regard, or are other factors, for example, work experience and software development, considered equally important? Correct. There is an emphasis on academic performance, but that's just one element of your overall application. So absolutely, any extracurricular activities or work experience that you have had in software development is highly regarded in your application. So on the software side, the initial part of your process is actually is a coding test. And we do ask for academic transcripts when you do apply. We're specifically looking on the software side of how you've performed in data structures and algorithm subjects, but we know the academic transcript is not the be-all and end-all of an application. So we do ask questions around your extracurriculars, and we do encourage you to use in your CV to give examples of projects that you've been working on, whether it's been through work experience, whether it is, personal projects that yourself, coding projects that you have done. And then from that, after that initial screen, the academic transcript probably doesn't have as much weight. After then, it's actually how you perform in our process. So there's a number of different elements as part of the process. So, you have an opportunity to sit down with the developer and design, you answer a question through the design and then actually code. You have opportunities to have more technical interviews, and equally, we have opportunities on the behavioral side as well. So in short, the academic transcript is just one part of it. Is important. We do look for smart candidates, but we know that it's not, it's too narrow-sighted to just be focusing on the academic transcript. There are so many more elements that we value in a candidate outside of the academic transcript. So this question, I think, is for Dave. Does IMC use other low latency languages like Rust, which attempt to control some of that undefined behavior in C++, or is there a dedicated effort to centralize around C++ and Java?
Yeah, another excellent question. The idea of using Rust is something that I think I've heard discussed ever since I joined. It hasn't taken off so far in IMC. And it's interesting to consider why that is. I think the bar is so high for it to achieve the same latency as we can with the C++ code that we have, that it's just a real challenge. However, if it could deliver on the promise of being able to get very close to that while offering better safety, that certainly would be of interest. So I think with something like that in IMC, it really waits for somebody to just become the champion for it and said, you know what, I believe in this. I'm going to spend some of my time doing a proof of concept, and we'll see what we can do. And the day that happens, it could spark quite a big change. So I'd say the dominance of C++ is not so much through a decision as the fact that, that real sort of disruptive proof that we can do something else hasn't come along yet. Also, as the industry has moved forward, and we're doing more and more work with FPGAs, I guess the attention on can we do better than C++ has also reduced somewhat, because for the very fastest work we're down in the VHDL, where Rust wouldn't help you anyway. But I always secretly hoped there'd be a Rust revolution actually in IMC. I haven't seen it yet. Maybe someone will join and they will lead the charge. Who knows?
Okay, we've got another question. Are there any use cases for just C? I.e., is there any time that C++ is considered too slow?
Also a good question. I think the answer is no, because really anything you can do with pure C, you can also, we would still call it C++, I suppose. It would just be a part of the C++ code that's using the pure C features. So when we talk about C++, it doesn't always mean we're actually trying to make use of classes and all of the object-oriented features. Some of the code you would look at in isolation and it would just look like C code. That is true. I guess the template metaprogramming part of C++ is very heavily used as well, so that we can try to express our ideas in a slightly higher level way, but still produce the optimized code that comes out. So that's probably the best way to put it, is that some of the code you could call C, or maybe C+, where it's just using those C style features of the language.
Looks like it's a final question that's come through. What tools does IMC use to carry out stress performance load testing? Is experience in load runner test suite desirable at IMC?
Yeah, interesting question. So let's see, most tooling we have in these areas would be something in-house, mostly because we're trying to generate conditions like there would be on the real exchange or something like that, and there aren't off-the-shelf systems that do that. But I suppose it depends what kind of stress and load testing we're talking about. So one thing we can do is record real market data that arrived on a particular day, and then in a lab setting we can replay that, but we can also maybe make some changes to that data or replay it at a higher rate and see what happens. Or for components a bit further up the software stack, where they might be exchanging messages with some other system, protobuf or ActiveMQ or whatever it might be. Similar kind of thing, except instead of network packets, we're generating fake data there. On the more of the sort of SRE role that Denia mentioned, there I think there's more scope for standardized tools, because we might not be thinking so much about the software behaviors as the overall system. How much data can we throw through this switch before everything falls down in a heap? And there, I imagine that experience with stress testing tools that are more sort of industry standard is definitely a part of the picture. Yes, and being able to make sure you don't run them on your production system, also very very valuable skill.
Excellent. That looks like it's the end of the questions. I have put into the live chat our careers team email address. If anyone has any further questions, please, I do encourage you to get in touch with us. But thank you all for your attention this evening, and special thanks to Dave for that really informative presentation. It's really valuable what you're able to share with students. So thank you so much for that, Dave. And everyone enjoy the rest of your evening.
Great, thank you.
Thanks all. See ya.